My name is Adi Eldar, and I am a product manager in Azure Data Explorer product team, responsible for advanced analytics, including time series analysis, machine learning, Python connectivity, and more. In the coming session, I'm going to present you these capabilities in Azure Data Explorer, also known as Cousteau. We are going to review time series analysis for anomaly detection and forecasting, following by clustering plugins for diagnosis, anomalies, and root cause analysis. Later, we move to the scan operator that is used for process mining and sequence analysis. And all these three are native capabilities in Azure Data Explorer. Further, I'm going to present you how can you embed inline Python or R in a Azure Data Explorer KQL query, and how can you connect to Azure Data Explorer from Azure Notebook, Spark, and so forth. At the end, we are going to have a few minutes for questions. Starting with time series analysis, so we have the make series operator to create a set of time series in Cousteau. And once you create a set of time series, the user can apply large family of functions on the time series, from simple functions like element-wise operations, adding, subtracting time series, through filtering, for example, moving average, differentiation, exponential smoothing, and so forth, simple statistics, and then regressions, linear, non-linear regressions in order to find change point, analysis in the spectral domain to detect seasonality, and up to the top level function for anomaly detection and forecasting. What's important to note that all these functions can be applied and optimized to process thousands of time series in a matter of seconds, and you will see it in my demo. Okay, let's jump directly to demo of this. So suppose I have a tabular, a table of, in this case, HTTP requests. We have the timestamp, we have the source location and browser and operating system of the HTTP request. If I want to convert it to time series representation, I need to feed it into the make series function. So let's see it, and I'll explain the function. So first we extracted here the start and end time in my data set. And then I take my table, feed it to make series, specifying a count aggregation. In this case, I don't have any metric, so I just can count the number of records in specific time bins. Here I specify what's the behavior in case I don't have any records in a specific time bin. So the default is just fill with 0. We also support fill forward, fill backward, or linear interpolation of gaps in my data. This is the timestamp in the aggregation column. From the minimum time to the maximum time, the granularity or the step size is 1 hour, and partitioned by operating system. So, and finally, I just render it. So what you can see it visually is that we have 3 operating systems, Windows 10, 7, and 8. This is an old data set. We have 2 weeks of data, and you can easily see the daily seasonality, Monday to Friday. You can see the weekend, Saturday, Sunday. You can see that the traffic of Windows 10 is much higher than the older operating system. And basically, this is the data that is going to be used for further processing, anomaly detection, and so forth. If we look on the data structure, we can see it's kind of pivoting, where we have for each partition, in my case, we only have 3 operating systems. For each partition, we have a single new record containing the vector of the timestamp. You can see midnight, 1 a.m., 2 a.m., and so forth. We have 2 weeks data, 24 hours. So the vector of the timestamp, this is the size of it, 336. And this is the number of records in each timestamp. This is what you see in the chart. Okay, so let's see some functions that can be applied on time series. So let's start with a simple time series which has some stable metric that start to drift at some point. This is a change point, actually. This could represent, for example, temperature sensor in IoT scenario where the air condition is broken and the temperature start to rise, or it can be exceptions that start to go up. In any case, it's a typical scenario of anomaly detection of streaming data where we have some look-back period with stable activity, and then something starts to go wrong. So we can run a linear regression in order to find the trend of this time series using the function series fit line. So in our case, we can see that indeed the blue line is the regression line. You can see that the traffic is going up. And if we look on the result, we can see that indeed we have a positive slope. There is a constant increase or constant trend of the time series. Note that we also have R square, which measure how good is the fit to the original time series. This is a number between 0 to 1, where 1 represents a perfect fit and 0 means there is no correlation between the line and the original time series. 0.79, it's pretty okay, but it's not perfect. Sorry for that. There is some issue with the rendering. So you can see that here we have a change point and the line is not doesn't fit perfectly the time series. Because of the fact that a change point is important for anomaly detection on streaming data, we also implemented the series fit 2 lines that try to find a change point by splitting the original time series to 2 segments and do the best fit for each segment. So we can see indeed that using 2-line fit, you can see that the blue line actually caught exactly the change point at this point, and this is a much better fit. And if we look on the results, we can see that now R square is almost 1. There is some noise in the time series, so it's not perfect 1, but almost 1. And we also have the split index, which correspond to the time of the change point. Okay, so by the way, this function can also catch in case we have a step jump. So for example, here I can apply it on a time series with some step, and you see that the step is caught exactly like before using 2-line fit. So just by using this single line and 2-line fit, we can build a simple shape detector that detects a gradual increase or step increase or decrease in a time series, and it's very effective for change point anomaly detection. Let's move to filtering, and here I present how you can do a moving average over a noisy time series. So you can see in red the original time series, and in blue after we did a moving average of 8 points. So each point in the blue line represent average of the previous 8 points of the red line. And things to note here that first of all, I define a user-defined function, a UDF, which I call series moving average. This can be stored on the database, but I can also embed it inline like here using a let statement. And inside it, I call the native function series FIR. FIR stands for finite impulse response filtering. It's a family of different filters. In our case, we just use a simple low-pass filter of moving average, but I can also use it to look on a derivative of time series or do a better filtering to detect specific shapes using this series FIR function. In a similar manner, we also have native series IIR function. IIR stands for infinite impulse response. It's a kind of recursive filter, and this can be used if you heard about exponential smoothing, for example. This is a recursive filter that can be applied in a KQL by using the function series IIR. Let's see some analysis in the spectral domain in order to detect seasonality. So in this case, we have a time series over a full month of data in 2-hour resolution. Again, it's a traffic of some HTTP service. You can see the daily seasonality, Monday to Friday, and you can see the weekly seasonality. We have here 4.5 weeks. These are the weekends, and these are the weekdays. By the way, also note that apart from the seasonality, there is also some positive trend. Week over week, the traffic is going up. And this is important, recall this, because when I'll present the anomaly detection and the forecasting, we're going to extract this positive trend in our model. But for now, let's see how we detect the seasonality. So I can use the function series periods detect. I feed it with the name of the column of the time series. What you see here in the chart is actually, this is the name of the column of the time series. And what I do here, I run the function, the series periods detect, specifying a range of seasonality. I'm looking for a seasonality, daily or weekly seasonality. So here I specify up to 8 days seasonalities. The reason I defined it, divided by 2 hours, it's because we get the seasonality in number of bins. So in this case, 8 days over 2 hours, this is the number of bins for 8 days seasonality. Running this function, the last parameter, by the way, actually tell the function I'm looking for the top 2 seasonality. So we can see that the top seasonality is the weekly seasonality. It's actually 84 bins of 2 hours, and it corresponds to the weekly seasonality. And for the function also return the score between 0 to 1, and we see the score here is 0.82. It's pretty high score. Everything above 0.6, it means it's a true seasonality. So we can see the top seasonality is the weekly seasonality, and we also have the daily seasonality, 12 bins of 2 hours each, which has a smaller score because the daily seasonality is broken over the weekend while the weekly seasonality is consistent. Okay, if I want to, for example, filter the daily seasonality, I can use this moving average, and you can see here in the red, you can see the original time series, and in the blue, you can see after I filter the daily seasonality using a moving average of 12 bins. And we can verify it if I run the function series periods detect on the original metric and on the metric after filtering the daily seasonality. You can see that on the original metric, we have both weekly and daily seasonality, while on the filtered metric, we have the weekly seasonality, but we don't have the daily seasonality as we filtered it away. Okay, let's see now how we do anomaly detection and forecasting on time series. We implemented a seasonal trend decomposition model for this, for anomaly detection and forecasting. This is a classical model that is used and is very easy to understand and interpret. And we implemented it very efficiently. You will see how it works on plenty of time series in a matter of seconds. So first of all, let me explain you the model itself before using it for anomaly detection or forecasting. So what I have done here, I just create the time series of this 1 month traffic, and I call the function series decompose in order to build this seasonal trend decomposition. And I I'll explain now the different components. So this is the original time series that you have seen for full months. You see here we have this daily and weekly seasonality, and you can see also there is some trend week over week, the traffic goes up. So the first thing that the function series decompose is doing, it tries to find the seasonality, and if it finds the seasonality, it builds the seasonal component. You can see it in red, this seasonal component. Then we subtract the seasonal component from the original time series, and we look for a trend. So you can see in light green, we have this positive trend that the traffic is going up week over week. We subtract the trend, and then we have the component that is called the residual. Note that the average of the residual is 0, and when we will run the anomaly detection algorithm, we will actually run outlier detection on this residual. The last component, if I add the seasonal and the trend, it's called the baseline. This is in light blue. And when I'll run the forecasting, it's just extrapolation of this baseline. So let's see how it works first in anomaly detection and then on forecasting. So for anomaly detection, we have a function series decompose anomalies, which is using behind the scene the base decomposition model that I just showed you. So let's see how it works to detect anomalies. So this is my original time series. And if I look for the anomalies, these are the anomalies. And you might wonder, for example, why are these 2 points are anomalous? It looks in the middle of the dynamic range. It looks legitimate. So recall that we calculate the decomposition model behind the scene. So if I show it and I zoom in, we can see in blue the expected traffic on Monday 6 p.m., which is here, while the actual traffic in red is much lower than the expected traffic. This is the reason these points are anomalous. Even though, without this decomposition model, we could never guess there is any problem here. In the same manner, you can see here on Tuesday 8 a.m. that we have a positive anomaly. The traffic is higher than expected because the expected traffic is in the blue for Tuesday 8 a.m., while the actual traffic is here. So by using this decomposition model, we can detect anomalies on top of the expected behavior for the specific time on the specific day of each time series. By the way, I can just comment this line and we can see how it works on multiple time series at once. So this is the time series that you have seen. This is the second time series with some negative trend, and you can see the anomalies. And this is a very noisy time series, and still we detect anomalies on top of the noisy data. Okay, let's move to forecasting. So the forecasting actually use the same decomposition model, but what I do here, we take the baseline and extrapolate it to get the forecast. So in red, you can see the original time series, but in make series, instead of building it from the minimum to the maximum time, we also had the horizon. We want to forecast the next 7 days. So you can see here, it's just filled with zeros. It's just placeholder to get the forecast. And the forecast itself, it's in blue. You can see this is the forecast of the next week. And if I take off the original time series and I show you this, you could never guess that the actual 5th week is a forecast. It looks very authentic and similar with respect to the same seasonality and trend of the original time series. By the way, when we call the series decompose forecast, so we need to specify, of course, the original time series to forecast, and also this parameter specify how many points we want to leave off the training and just forecast, because we want to train the model on the real data of the 1 month, and we want to score or predict also the next week. So here we specify that we leave off the training all this placeholder for the next week. Okay, so now I want to show you how this function can be applied on thousands of time series. And for this, I have a table from SQL Azure from few years ago, actually subsample of the records. And what we have here, we have a data read metric, and we have some triplet of location, operation, and database that represent a single instance of the service. So first of all, let's look on this metric on the range of this table to look if we see any anomaly. So it looks pretty okay. We have some fluctuation of the read count. This is a data of 4 days. We present it in 1 hour resolution. It looks pretty okay. But suppose we have some issue with some of the instance of the service. Suppose we deploy a new version and we have some issue. If we would have to wait until the anomaly is reflected in the global aggregation, it means that plenty of instances of the service are already have this faulty version. So it makes much more sense if we just want to analyze each time series of each instance of the service by itself. So first of all, let's see how many instances of the service we have here. So I can do it by just this simple calculation. We can see that we have more than 18,000 time series, more than 18,000 instances of this service. If I want to create now a 18,000 time series, all I have to do is to add this by clause by location, operation, and database to my make series. And because I cannot render all of them, I'll just randomly select 5 time series and chart them. And let's look one by one. So we see this single instance has some seasonality, and this one has a different pattern, and this one has another pattern, and another seasonal pattern, and another one. Overall, each time series behave differently. And what I want to do now is actually to try to detect the top 2 instances of the service where the read count was normal and dropped to almost 0. And let's see how I do it. So first of all, let me run the query, and then I'll explain the logic. So what we can see here, we can see here indeed that this instance, for example, the read count was normal and dropped almost to 0. And the way we detected it, we created the 18,000 time series. We filter time series with empty bins using this simple helper function. The reason I filter time series with empty bins, it's probably testing instances. I do not want to find anomalies on testing instances, so I just filter them off my data. And then I run the linear regression, the single fit line, and you can see this is actually the linear regression. Even though we have a change point here, using a single linear regression, we can see it's a very negative slope. Then I select the top 2 with the most negative slope, and finally I run the series fit 2 lines in order to find the change point. So you can see this is a single time series that we selected, and this is a similar, the other time series that we selected. And if we look on the tabular representation, we can see that indeed this is the most negative slope of out of the 18,000 time series, and this is the second most negative slope. And just by running a simple 8 lines query that ran in about 1 second, we detected 2 time series that where the read count was normal and dropped abruptly to almost 0. And this pattern can be used for health monitoring, for streaming data, and for example, we have customers from the IoT market where they have thousands of devices, and you can run every 10 minutes, for example, run this kind of logic using this fit two lines, or series decompose anomalies that you have seen in order to detect anomalies out of plenty, thousands of time series. Okay, so once we detected anomalies, it might be true anomalies, it might be false positives. So let me jump back to the presentation for a minute. So we showed the time series analysis capabilities, and now what we want to do once we have potential anomalies, we would like to diagnose these anomalies and try to get the root cause of these anomalies. And we can do this using plugins that are part of KQL. I'll present in this session AutoCluster and diff patterns. AutoCluster used to clusterize a single record set, and diff patterns is used to find the difference between two record sets. You also have the basket analysis, a priori algorithm, and the diff patterns text. I'm not going to present them during this session due to timing. So let's see how we do clustering of anomalies. So for this demo, I have a table of exceptions from TFS, its internal Microsoft service from a few years ago. So we have the timestamp, and we have few dimensions of each exception: the scale unit, the region, deployment, etc. So first of all, let's see how the time series of the exceptions looks like. So we can see that we have, this is a weekly data. So you see the typical Monday to Friday and the weekend. But on top of the seasonality, we have these spikes on Monday afternoon and Tuesday afternoon. And if we look here on Tuesday, 3 p.m., we have a spike in the exceptions. And in this demo, I want to understand the root cause of this spike. I don't care whether this anomaly was automatically detected, or it could even just someone call and say, we have an issue. I want at this point just to analyze the root cause for the spike at Tuesday, 3 p.m. So this time series is charted in 10-minute resolution. First of all, let's try to look in higher resolution, in 1-minute resolution, around the problematic time window. So we can see that it's a very sharp spike of the exception at exactly 3 p.m. On that date. So the next logical thing to do, let's just look on this exception. There are not too many in this simple case. We have less than 1,000 exceptions. If we look on this exception, we can see different scale unit, different regions, deployment. It's not easy to understand what's going on. Do we have any common denominator of these exceptions? So it's much easier to do it by feeding it to the AutoCluster plugin in KQL, and instantly it tells us that 2/3 of the exceptions are coming from scale unit 7, this region, this deployment, etc. So AutoCluster is very effective. Just you have a data set, you want to find clusters or patterns or segments that represent the data. It's a clustering algorithm, but it's not full partition. There might be records that do not belong to any cluster, and there might be records that belong to few clusters. It's unsupervised learning. The idea here is that we want to give the guy that try to analyze the spike a good starting point to further dig through the data. And the fact that 2/3 of the exception have all these common dimensions is very useful. And to get this insight, without AutoCluster, you need to have plenty of domain knowledge and sort the data by scale unit and select and then another dimension. AutoCluster does this mining on multiple dimensions and just give you a short list of candidate clusters to continue the investigation. But AutoCluster is not perfect because suppose this segment doesn't represent the anomaly time window, but just represent the global distribution of my data. So in that case, I can continue the investigation, but this is just all my data might come from this segment. If we go back to look on the 1 minute chart, AutoCluster analyze what happened in the 2 minute anomalic window, but what we found might represent my full data set. And for that reason, we developed these patterns that actually try to find patterns in the anomalous time windows, but compare them to patterns in the baseline normal window. And if we find patterns that are different between the anomalous and the normal windows, they are more likely to be connected to the anomaly. So let's see how we run these patterns. So we just define here variables. These are the times of the anomalous time windows, the 2 minute of the spike. And here I define a baseline 8 minutes before. I select my original table. I filter for exceptions that occurs either in the anomalous time windows or the baseline window. I add a binary column for each exception for its source, whether it's from the anomaly or the baseline window, and I feed it to these patterns, ask it to split it to 2 subsets, the anomalous and the normal exceptions, and find the patterns that differentiate between these 2 sets. And when I run it, I see that the top pattern is the one that I already got from AutoCluster because it's scale unit 7 and this region. And even if you recall, this is exactly the same number that we got from AutoCluster, and this is the 2/3 of the exceptions coming from that segment. But what we have now in addition is that we can see that only 1.7% of the exceptions in the 8 minute baseline window came from this segment. So the difference, this minus this 64 percentage point means that it's very likely that this segment is responsible for the anomaly in the 2 minutes window. So let's verify it. So first of all, let's recall what we looked for. We looked to understand the root cause for the anomaly on Tuesday, 3 p.m. And what I do now, I will split the chart to 2 charts. One is the chart for all the records whose origin is from this segment that was detected by this pattern from scale unit 7, this region, etc. And the other chart is all other exceptions. And when I do this, we can see indeed that the spike in the exceptions was due to records from that segment. And without it, we see the normal behavior of Tuesday afternoon. And when we cross-check with our colleagues at the VS Online team, they were very impressed because we detected the root cause. Actually, it was a bad deployment that was rolled back. And we detected it just by running these patterns without any domain knowledge. So to summarize this part, we have a time series analysis function to detect anomalies and on thousands of time series in near real time. And once we have anomalies, we can analyze them automatically using diff patterns. In case diff patterns find a differentiating segment, we can send an alert and give also all the information from diff patterns to further diagnose the problem. In case diff patterns doesn't find any specific pattern, we can just cancel it as a false positive, and that's it. So this structure is actually used by customers both within Microsoft and also external customers for building a pipeline for health monitoring of either cloud services or IoT monitoring, and it's very effective and very efficient. Okay, let's move on. The next thing I'm going to present very quickly is the scan operator. This is, I would say, the most advanced operator that we have in IDX, and it is used to find a sequence of events that occur in a specific record set. It can be used for process mining or for user analytics, funnel analysis, and I'll present you some of the use cases for the scan operator. Okay, just a minute. So, moving to this demo. So first thing is to show you how you can do recursive functions using scan operator, for example, cumulative sum. We have a native function, CumSum, that we can use, but I want to show you how you can do it using scan. So what you do in scan, you actually run all the data, and you can define sequence of steps that each record that is processed pass through the different steps. In this case, we have a single step. There is a predicate to decide whether the record matched the step. In our case, we want to match all the records. And then there is some action to do. In our case, we extended the schema with cumulative sum, initialized to 0. And what we want to do in each step is just to update the cumulative sum with the new record. So note that we can refer the previous sum and just add the new value. So we have cumulative sum using scan. If we want to fill forward some string values, because we can fill forward a numeric value using time series function, but for string values, for example, I have some states, I want to fill them forward. I can also do it using scan by this similar logic. Just in case I don't have a state, I can just copy the previous state, and you can see the input and the output. What I want to show you now, it's a more interesting scenario where I want to do some funnel analysis. And funnel analysis is actually used for usage analytics. In our case, we have a tentative website for purchasing, and I have users log in and go in the campaign landing web page. They can browse different products to see product details, they can add to cart, and they purchase. And I want to see how many users started this funnel, campaign landing, how many continue to product details, add to cart, and final purchasing. And the way I do it, let me run it, and then I'll explain the logic. So what we do, what we can see here is that 15,000, more than 15,000 started the campaign. Half of them continue to product details. Here we have a big drop of only 5%, continue to add product to the cart, and again, a big drop, only 16 people finish and purchase. So this is the usage analytics. In a similar manner, you can build a sequence of events in IoT or other scenarios. Let's see how we did it using Scan. So we took the original page view table, and first of all, we partition it by users because we do not want to mix events from one user with another user. So we partition it by users. So in this context is for each user. We order by timestamp. And here, what we do, we have the first step, campaign landing. And then the next step is in case the user moved to product detail. And here you can see the predicate is not like before, it's not true. It really, we need to check that it's product detail. And also we want to make sure it's not too far away from start of this session. So up to 10 minutes after campaign landing, the user need to go to product detail. In that case, we move to the next step. The next one, in a similar manner, it's add to cart, where we want up to 15 minutes from product detail until add to cart. And the final step is purchasing, also up to 15 minutes after add to cart. And after we have this sequence of scan, what we have to do, we just do summarize of the by each of the steps. And we can see that we have indeed this 15,000 campaign landing events followed by product detail and so forth. So usually the pattern of using scan is partitioned by your device ID or user or whatever entity you have for a session or things like that. Then you have the logic of the scan itself. And then you have the post-processing of scan results in order to find like this funnel, or you want to find specific sequences and so forth. For further information about scan, you are welcome to go to the blog in the tech community about the new scan operator, where you have many more demos and a lot of explanation. For example, here I use the scan operator to find the rallies of top stocks, the longest rallies, and very nice demos in this blog. And of course, the official documentation, you can get further information about the scan. Okay. So up to this point, we talked about capabilities, native capabilities in ADX, in KQL. But even though we have some machine learning, time series, sequence mining capabilities inside ADX, there are huge amount of algorithms of machine learning and others in the community. And what we have done, we open our platform to run Python from within KQL query. And you will see it in a minute, but it's very nice and easy to embed Python code inside your KQL. Some details, the Python run on secure containers on the same compute nodes. You don't have to pay for additional hardware or to allocate extra nodes. It just run on the same compute nodes that the cluster is configured. It can run either on a single node or in a distributed manner on multiple nodes, where each node processes its own data and computation is done near the data. It's very efficient. The image is based on Anaconda 5.2 plus additional deep learning packages, and you can install custom packages if you need. You can use it to score machine learning models, and you can even debug it using VS Code. it's a very nice way to develop Python inside ADX. Before moving to demo of this, I also want to mention a KQL magic, because when I'm going to present you how you do supervised learning in ADX, I'm going to do the training in Jupyter Notebook and the scoring using the Python inside ADX. So in Jupyter Notebook, we use this KQL magic extension in order to pull or push data from ADX to my local notebook. And this is a very easy way to connect to ADX data from notebooks. Okay, so let me jump directly to demo both the inline Python and the use of KQL magic in Jupyter Notebook. So suppose this is a simple Python script. When we pass a table from Cousteau to the Python, the table is mapped to a pandas data frame, which is named df. You can see it here. The Python logic need to store the resulting table in a pandas data frame, which must be named result. And the last keyword, reserved keyword in the Python context, is k-args. We can pass a dictionary of key value pairs of parameters to the Python script, and this dictionary is mapped to k-args Python dictionary. So this simple Python script actually tells something like, take my input table, copy it to the output, and create a new column in the output, y column, which is the original x column to the power of x, which was passed as a parameter. So if I try to run it in KQL, this is just a syntax error. It's not even a legitimate string in KQL. So the first thing that I need to do is to fancy it using a triple backtick like that. So now if I try to run it, you can see this is a multi-line string in Python. Now, in order to run it, so suppose I have this is my original table, 1 to 10. To run it, I need to feed it to the evaluate Python plugin. The first parameter, I need to specify what's going to be the output schema. In KQL, each operator needs to declare what's going to be the output schema in order to do the query planning. So in our case, we say the output schema is going to be the input schema plus a new column y. So this star is actually a shortcut for the input schema. In our case, it's only the X column, so it's simple, but if you have a Y table, it's very convenient to specify this using the star notation. And here I say I have a new column of type integer that returned by the Python script. Here I specify a reference to my code. I could embed it directly or just put it in a let statement and refer it. And this is my dictionaries that I usually create using the pack function. These are just key values. In our case, it's a single exponent that I pass to the Python script. So let's jump directly to more interesting demo of k-means from scikit-learn. I skip a lot of demos here just because of time. You have them. I'll send reference to these demos. So for the next real demo, I use a public dataset from UCI repository. It's actually IoT dataset where we have temperature, humidity, light, CO2, and humidity ratio. And we want to predict whether the room is empty or somebody is inside the room. My first demo, I'll just take this measurement and run k-means on these 5 columns. And the demo after, I'll actually show you how you build a classifier to predict occupancy. This is a table not too big. It's only 20K rows, but we can run the Python on hundreds of millions of rows without a problem. And let's see how the k-means is working. So first of all, I'll run it, and then I'll explain you the Python itself. So to run it, here I define, I want to do k-means of 5 clusters. I take my original table, occupancy detection. I add a new column to get my cluster ID. So you see it here. And then I call the function k-means function. Using the invoke mechanism, it's in order to call tabular function that operates on the full table. I feed it and use the invoke operator. And this function, I supply the number of clusters, the list of the feature columns, and the name of the column to put the result of the clustering. And finally, I just show you 10 records of the output. You can see we have the original table, and we have also cluster ID. It's a number between 0 to 4. So it's indeed the clustering. Let's see how the Python works here. Okay, so this tabular function, as I said, it can be defined just here inline, or it can also be stored on the server. So if we look here, for example, you can see that I have this function also stored on my database, but for demoing now, I prefer to have it here. So what we do in the k-means, you can see at the end, I take the input table. By the way, when I call a tabular function, the table itself is the first parameter that is passed to the function. It's like the self pointer in Python or this in other languages. So this is a reference to my table. So I can just take the input table and feed it to evaluate Python. If we look on the Python code, first of all, here we created the dictionary of the parameters to pass to the Python. My best practice is just to use the same names for the key and the values. So this is the number of clusters. This is the name of list of the feature column, and this is where to put the result of the clustering. If we look on the Python code, by the way, this dummy if1 is just in order to avoid indentation error of the Python, because Python, if I don't use this dummy if, I should have put all my Python code adjusted to the left. So just for pretty print, I pushed it and put this dummy if1. Anyway, inside the Python, first of all, we import k-means from scikit-learn. By the way, the Python sandbox automatically imports numpy as np and pandas as pd, but it doesn't import scikit-learn, so here I import k-means. Here I extract the parameters from my dictionary. This is the number of clusters, this is the features, this is the cluster column. Here I create the k-means object. I slice my data frame to contain only the feature columns. I run the fit function. Finally, I copy my input table to the output, and I override the cluster column with my clusters. Very simple. I just ran k-means by leveraging scikit-learn and use it from within KQL. For the final demo, I want to show you how you can do supervised learning, and I use the same data set of the occupancy detection, but now I want to predict the occupancy. So you can actually train the model inside ADX, but if you want to to select the best model, hyperparameter tuning, etc. It's not very convenient to do it using KQL because it's not a data scientist IDE. You can probably use VS Code or PyCharm or Jupyter to do it. And I'll show you how you can do it in Jupyter. So this is my Jupyter notebook to build a classifier. The first thing I talked about KQL Magic extension to Jupyter. You need to install KQL Magic in your environment. I already done it, so it's commented. It's a one-time. In your notebook, you reload this extension, KQL Magic, and once you reload it, you can just connect to Cousteau cluster by this magic command, %KQL with Cousteau. This is my cluster, this is my database, and this is my authentication method. By the way, using KQL Magic, you can also connect to Azure Monitor, Log Analytics, and it's a very convenient way to fetch or push data from services that use Cousteau as their database. So in order to retrieve my occupancy detection table, I use this simple syntax, %KQL, occupancy detection, and I want to store it in a pandas data frame df. So once I did it, I now have in my local Jupyter the same table that you have seen in Cousteau, where I have the measurement and the 20K records. Now I simulate the process of building a supervised learning model, a classifier. So I look on my splitting my data to training and testing, and I'm trying here to build the best model out of decision tree, nearest neighbor, naive Bayes, linear regression, and so I create instances of these models. I run the training using the fit function for each of the model, and now I look what is the accuracy of each of the model. We can see that the best model is the logistic regression model. We have more than 98% accuracy. This is a very simple data set. Usually, data scientists don't get this high accuracy, but for demo, it's okay. So this is the best model, logistic regression. I look what is the accuracy on the testing set. It's also logistic regression is the best, almost 99% accuracy. And now I want to export my trained model to ADX to do the scoring using the Python sandbox on ADX. So to export it, this is my best practice. I define a model table, which I call ML models. And for that model, I call it occupancy model. CLF2 is my trained logistic regression classifier. And what I do here, I serialize the model. So I pickle it and convert it to a string. This is S model. It's a string of my trained model. And now I create a very simple one-line data frame containing the name of my model, occupancy, the training timestamp, and the string of my serialized model. And all I have to do now is to push that record into my model table, and I can do it using my magic KQL with this simple .set or append query. Again, it's a tricky query, set or append. It's really cool. It takes a Python variable, set it in a Cousteau variable, and run it and put it into the model table. If we go back to Cousteau, so first of all, let's see our model table. So we can see indeed we have occupancy, we have the training timestamp, and we have our serialized model. Just a minute, let me show you. You can see this is not big model, it's just logistic regression. This is the serialized model. In order to actually do the classification, let me run it and then I'll explain. So we have this occupancy detection, I select only the testing instances. I extend with the column to get my prediction, and I call my classify function, supplying the name of the model table, the name of my model, list of the feature column, and where to put my predictions. And finally, I create two result sets. The first one is the confusion metrics. These are the correct classification. These are the misclassifications. And the second one here, this is the accuracy. And how we did it is just in a similar to the k-means. We have this function. Here I get my model string from my model table, the latest model. I pack it in my dictionary to send to the Python. So I send the string of the model, the feature column, the prediction column. Inside my Python, I extract the parameter, and I reverse the process that I have done in Jupyter. I take the string of the model and convert it to binary. I unpickle it to a trained classifier. I slice my data frame to contain only the feature column. And finally, I run the prediction, copy the input data frame to the output, and override the prediction column with my predictions. So what you have seen here, how easily we can train a model outside ADX and score it inside ADX. And this is very nice and used by some of our customers. Okay, I'm almost done. The last thing I want to talk is about we have also SDK for Python and R, and we have a connector to connect to Spark to pass to and from Spark efficiently big amounts of data. We support Parquet, and we support external tables, Parquet file and others in order to connect to this data set which are not in Custo. That's all for now. Thank you very much, and feel free to contact me for any questions. Thank you.